So,
Thank you, Zal. It's very nice to see a bunch of familiar faces and also a bunch of unfamiliar faces here. That's always encouraging. So this talk will be slightly mathematical because really it's going to be focusing on a sort of surprising story, which started out in a biological observation, led to mathematical developments, which now we're beginning to bring back into engineering. And actually, I think gives a very surprising result as to the smoothness of systems with multiple collisions. But maybe someone will tell me that this is obvious, and that will be fine too. Okay. So general structure of this talk, I'll start with credits so that don't shortchange everyone, and then I'll talk about this class of systems, event-selected systems, and some of their mathematical properties, and then their stability properties, perturbation properties, and will lead up to this surprising result of smoothness and the experimental system we built to test it. And those of you who do experimental work in robotics or biology know that experiments are a lot more interesting than you'd think. There's a lot of work to make those happen. So first, credit where credit is due. Most of this theory I developed with Professor Sam Burton from University of Washington back when he and I were both grad students in Berkeley. We started thinking about this and got the math published in 2016. And so that sort of gives you a sense of the art. A lot of the key results that we have here were done by my former student, Dr. George Council, who went on to Carnegie Mellon and is now in Ford Robotics. The robot was built by Taylor, who is now a master's student in University of Southern California, but started out as an undergrad in my lab. And Marian Anderson, my current PhD student, is the person who did most of the relevant work here. I'm just promoting other people, basically. And of course, thanks to all the funding agencies that participated in the history of this project, which has been fairly long. So my lab, the BIRDS lab, BIRDS, by the way, doesn't have anything to do with birds. It's bio-inspired robotics and dynamical systems. We do all sorts of things. We study animals. We do math and methods when we have to. Although I'm trained in math, I don't like doing math unless someone else hasn't done the math for me. This is one of those cases, unfortunately. And then we build a lot of robots. And so there are a lot of things we do. In this talk, we'll be talking, well, I think I might not even get to the horse stuff, but we'll be talking about some of the math and the hopping robot there. Okay, so let's talk about event-selected systems. And this is a little bit of a participatory exercise. So I'm showing you some animals moving around. What do these gaits have in common that's sort of mathematically weird? Let me run that again. So gait, how the animal is moving. I want you to notice that two legs are hitting the ground at the same time for the dog. 3 legs are hitting the ground at the same time for the cockroach. Now, if you're a mechanical engineer and a hybrid systems person, so these are multiple contact gates, multiple contacts happening at the same time. If you're a hybrid systems person, you think of this in terms of what are called guards. Guards are surfaces that we use to separate different regions of smooth dynamics. And each leg hitting the ground is a condition, which is basically a guard crossing. So what we have here is a gate that crosses 2 guards at the same time for the dog, or 3 guards at the same time for the cockroach. If you're a hybrid systems person, you really don't like multiple guards being crossed at the same time. None of the textbooks you'll find have much to say about this. Before we did our work, I think the most anyone had done was looking at double guard crossings and not really exploring those very deeply. So let's recap for a minute why we use hybrid models at all for these sorts of problems. Well, because of this idea that physicists call a collision. What's a collision? It's something where we know the input state and we can deduce the output state. We don't care about all the mess that happened in between because we have enough invariance to constrain the outcome. So all of you have probably done your undergrad. Elastic collision, you conserve energy, you conserve momentum, you know what the outcome is. You don't care about what happened when those two things hit each other. The outcome is predetermined. That's in general the theory of collisions, right? We reach a predictable steady state and we avoid all the complications that we might otherwise have because we like this abstraction of rigid bodies that don't actually exist. You'll see that that plays a role here. Acoustic propagation through the bodies, which happens during a collision, plastic deformation, surface interactions. There's all sorts of complicated things that we want to avoid modeling. by using collisions and hybrid systems. But it turns out you can have all sorts of hybrid dynamics. So the most general form of hybrid dynamics is you have an arbitrary state machine. The guards represent transitions. So if we start here, if we cross guard number 1, we have a new state. If we cross guard number 2, we have a new state. If after 2 we cross 1 again, we have the 2-1 state, and here we have the 1-2 state. Basically, each history could have a completely different dynamic. Okay. At the other extreme, you can have what are called complementarity systems. So those are used often in simulation of multi-legged systems. For example, work by Posa and Pedrake, they use a lot of complementarity systems. There, each guard only gives you an additive effect. And so if you go through B, you have F plus B. If you go through A, you get F plus A. But if you go through the second guard, what you do is completely determined. It's going to be A plus B. There's no more freedom in the system. Okay, it's completely determined. The event-selected system we work on are somewhere in the middle between that. What does it mean? The dynamics you experience is going to depend on the set of guards you've crossed, but not on the order in which you cross them. So if you cross 1 and 2 or 2 and 1, you're still in a state where both of those have been crossed. You're going to have the same dynamics, but those dynamics don't have to be the sum of the dynamics in 1 and the dynamics in 2. Okay, why do we care about that? Well, imagine the problem of catching a basketball. There are 10 fingers. You don't know in which order these fingers will touch the basketball. But you do know that eventually all will be in contact with the basketball. Well, in terms of contact states, you have 1,024 contact states. Each finger can be in contact or not in contact. But if you looked at all the histories, you have 10 factorial histories, over 3.6 million possibilities. This may be doable. This, not anytime soon. Okay? So the reason is when you start having lots of collisions, which happens in manipulation or multi-legged locomotion, this is a much simpler world to live in. But I also want to say there is a sort of physically intuitive way to think about why this happens. So imagine we have this two-legged creature and it's going to hit the ground. So the first foot hits the ground. And the body's still continuing with its momentum. And so this leg gets compressed because it can't actually enter the ground. If we're living in the world of rigid bodies, this leg has to relax back to its original length because it's rigid. And in this process, the effect is felt by the entire body before the second leg touches down because the body is rigid. And the problem is that the results from that can be complicated. They can sometimes be inconsistent. Here are two papers one from 2010 and one a little bit older, that show all sorts of weird inconsistencies that happen when kinematic chains collide with stuff. Okay, so the rigid body assumption generates a lot of problems, and that is because there's really a double limit here when you have multiple collisions. What's happening faster? The relaxation of the body to its rigid shape, or the interval between the collisions? And so the case I'm going to be talking about is the limiting case where the interval between the collisions is so short that the body is effectively not rigid. But I don't need to model those details. I'm just taking the double limit of collision interval and body relaxation in the opposite order than the folks who do rigid body dynamics. So that's one way to think about the theory of event-selected systems, is it's really talking about collisions that happen so rapidly together that they don't have time to propagate through the body fully. Or if you think about it differently in the context of what I did before, it's really a soft body result. This leg hit the ground, it's generating some force. Now the other leg hit the ground, and it has its own additive effect on the center of mass. Both of the legs have interacted, but the center of mass is still continuing to move with its inertia and being affected by those forces. So that's a different way to think about why event-selected systems are relevant. So let's talk a little bit about the mathematical properties. And by the way, all of this stuff is in this 2016 Applied Dynamical Systems paper. So the idea of event-selected systems is you have a region of state space where you have some guards. they intersect at some point rho. And what we demand is that the flow is smooth in each of the domains, in each of the domains between these surfaces. And furthermore, and this is a somewhat weird condition, you might think at first, but I can, if anyone's interested, I can explain why that condition is, can't say it's strictly necessary mathematically, but without it, very bad things can happen. All the flows have the property that they are monotone with respect to the various guards. So if I have some guard function that has a zero level set at the guard, the Lie derivative of these guard functions are all positive, strictly bounded from below. That means that all the events will eventually happen. And once they happen, they can't reverse. You can't hit the ground and bounce back up. If you want to do that, you have to treat that as two different guards. And so what you have here is you sort of flow through.
So is this sufficient condition or necessary?
This is a sufficient condition, but I can show that very mild relaxations of it can cause very bad problems. Okay, so one thing you could immediately do is you could think of changing coordinates and writing the coordinates. This is actually not with respect to touchdown time. I'm sorry, that's a typo. It's respect to the level set functions. So if I rewrite the coordinates here in terms of the functions that define these surfaces become coordinates. They straighten out, and I've just deformed my dynamics a little. So far, so good, but I've removed a bunch of complexity. Now these are not arbitrary surfaces, these are just hyperplanes. And now I can do the next step, which is zoom in on the region where things are interesting. And in that region where things are interesting, when I zoom in here, because these are smooth functions, they become more and more constant. Until eventually I can think of this as being hyperplanes and piecewise constant vector fields. And so what happens is the complexity actually reduces. It becomes just a piecewise constant vector field in different orthos. And if it's piecewise constant, I can solve in a pretty simple way what happens, which is if you enter through this surface and the piecewise constant vector field is like this, I'm just going to follow a straight line until I go out the other surface. So it's a projection operator, the linear projection operator. So what happens is each domain actually adds a single projection. And the only thing that happens when you're close to this multiple collision situation is that the order of the projections changes depending on where you are. And in fact, although I won't show you guys the proof, we can actually prove that under very mild conditions, all n factorial orderings will occur. Not only are they possible, but they actually will occur. So the orderings of these projection operators are pretty important. But I want to introduce first two other important mathematical building blocks. One is the class of functions that are called PCR functions. PCR functions are continuous functions that are made out of CR pieces. One intuitive example of how you generate PCR functions is PCR functions are an extension of the closure of smooth functions under pairwise maximum. So if I take the pairwise maximum of red and blue, it's going to be smooth here. It's going to be continuous at the boundary here. It's going to be smooth here, smooth here, smooth here, smooth here. But each piece is met at a corner, right? We have these little corners in between them. The PCR functions are sort of the multidimensional generalization of that. So the important thing to remember is they're continuous functions that are made out of smooth pieces. And it turns out that there's a pretty interesting mathematical theory for those. And it relates to this idea. So I'm sure everyone here has taken analysis and knows that about directional derivative. So a function is directionally differentiable if you can take this sort of expansion. This is the directional derivative. We have a scaling here. We take the scale to 0, and it has a derivative in the direction h if this limit exists and is 0. And if this limit exists and is 0, the directional derivative is df. There's a slightly less flexible notion of derivative where we change the limit. This is called the Bouligam derivative, where the h here is a vector, and we take the limit of h to 0 as a vector. And if you do that, it turns out that for PCR functions, this limit will always converge. When it converges, when the Boolean derivative exists, it actually is the same as the directional derivative, because the directional derivative is just one particular way to take this limit. But there can be cases where the directional derivative exists and the Boolean derivative does not. But the interesting thing about the Boolean derivative is that Boolean derivatives together with PCR functions recapitulate a lot of the standard theory of analysis. You have the chain rule, you have the implicit function theorem, all these standard building blocks of analysis exist there. Yes?
When you take this last derivative, do you change the direction of h or keep it?
You're allowed to change the direction of h because you're taking h as a limit to 0 as a vector. Yeah. So that's exactly the key point of what makes it different than a directional derivative. And so you can really think of this because of the nature of this function. This can only depend on the direction of h. It can only depend on the direction of h. You can think of the Boolean derivative as sort of a map from the unit sphere. But unlike a regular derivative where it's enough to know it in d directions, for the Boolean derivative, you need to know it on the whole sphere to know it. But it's going to be continuous. And in a moment, I'll help visualize this. But one of our key results for event selective systems, as they were defined before, is that they have a unique PCR flow. So they have a flow, just like regular ODEs do, but instead of having a smooth flow, their flow is going to be PCR. So really important, it's going to be continuous. Okay, space doesn't get ripped apart like general hybrid systems can rip apart your space. The impact times, the times it takes you to reach the events, are also defined in PCR functions, and unique maximal flow exists. So basically, this is the standard ODE theory that you learned for right-hand sides, which are Lipschitz in your ODE class. But now we have functions that can be discontinuous on the right-hand side as long as they obey the event-selected condition. So this is very interesting because we've basically expanded our notion of the class of systems in such a gentle way that we haven't lost the power of continuity of the solution and the ability to make series expansions like Taylor series. So what does this look like? So let's take the flow map, and locally, that Boolean derivative is going to be a composition of projections. So if we take a 3D system, so imagine this is sort of looking down the diagonal of the cube. We have a 3D system. It has 6 orderings that can occur. Each of them can have its own linear behavior because it's the derivative of a smooth function. But it has to be continuous at the boundaries. So whereas a conventional derivative will take a circle to an ellipse, right? That's all a linear function can do. It can sort of squeeze in some directions and rotate. The Boolean derivative takes you to this sort of Frankenstein monster made out of multiple ellipses. It's made out of pieces of ellipses that have to meet continuously on the boundaries of the domain. So it's a much more complicated object, but it still has the property that it is a first-order approximation like a derivative. A slightly more illustrative 3D example. Now we have a circle of initial conditions. You can sort of see that the transition manifolds here, the guards, are just perpendicular planes. If you look down the diagonal, you see again the sort of Frankenstein monster that's made out of pieces of ellipses. So that's sort of where we expanded to. Another important result, and yeah, this is a whole page of frightening math, is the dynamics are structurally stable. This is a really, really important property because it means that if we have our model wrong, if we have the equation for the guards wrong, if we have the equations for the dynamics wrong, the true behavior will be topologically similar, will be very close to the behavior we got from our wrong model. So without structural stability, basically, it's not a useful class of mathematical models for engineering because it might be too fragile. So although this is a horrible bit of math to prove, it's really important to make sure that this is there.
What does structural mean for you here?
So the strict definition here is that you need to define over what function space topology you're dealing with. And structural stability means that the flow as a function is topologically conjugate to the flow at the point you started. So there's a sort of continuity from the initial value problems to their solutions. It's sort of a continuity between function spaces, which says if you change your problem a little bit, your flow only changes a little bit. If you want to think about where that doesn't happen,
like changing in parameter space.
yeah, or changing in parameters. So for example, if you have bifurcations, that doesn't happen. Those are places where you don't have structural stability. You make a small change in a parameter and the system does something completely different. That can't happen here. For these systems, small changes in parameters.
But does that imply weakness? That you always have to have a unique attractor?
So you could have structural stability without uniqueness, but then what you mean by that exactly is even trickier. You know, this is...
You excluded bifurcations.
Well, okay. This is a much bigger question in an analysis and dynamical systems
A
theory.
buckling problem will have three solutions.
I mean, buckling, right? But buckling actually has an infinite series, right? You could have buckling at one point. You can have multi-order buckling.
Minimal set will be a pitchfork or three solutions.
Yeah, and so at the point of buckling,
Structurally stable.
it's not structurally stable at the buckling. At the buckling point, you have two solutions. One goes right, the other goes left. And you don't know which you'll get. Small perturbations can take you from bending right to bending left.
Okay, and you have to exclude that.
No, I'm not excluding it. I'm saying my assumptions
Okay.
provably exclude it.
Okay.
That is, these systems are well behaved in some sense, where if you got the model wrong, they won't buckle in some weird way and give you something completely different. So sort of the illustration of structural stability, I have a system, this set of initial conditions goes to that. I was completely wrong. Instead of being these nice straight lines, these are these wiggly lines and slightly different arrows. Then I go from that to something else. But that something else is not torn apart. It's not fundamentally different in a topological sense from what I had before. It's just a deformed version. And really, one way to understand what's happening in these systems is you can think of these surfaces and look at the impact times, the time it takes for each guard to happen. And it turns out that if you have enough guard, you can just rewrite your entire space just in terms of the times it takes for events to happen. Why is that a good system of coordinates? Because in that system of coordinates, everything becomes simple. All your flow is diagonal because time flows the same way. So time flows 1, 1, 1, 1, and all the coordinates, 1 unit of time per unit of time. All your guards are just hypersurfaces. So really the existence of PCR impact times, the existence of impact times being a nicely behaved function implies that there's a map that rectifies everything. And the behavior of the system is like the behavior of a flow box. Okay, so nothing bad can happen there basically because we have this nice conjugacy. We have a PCR conjugacy that takes the dynamics in a real system into a flow box, and nothing interesting is happening in the flow box. Okay, I'm almost done with all the annoying math, and we'll get back to mechanical engineering in a bit. We need to do one more thing, and that's talk about stability, because really that's one of the main things we care about in robotics and engineering in general, or in understanding biological control. So how do we do stability in smooth systems? In smooth systems, if I have some orbit phi, and I want to look at how the outcome of phi changes by changing the initial condition x, I have this, this orbital derivative where I take the derivative of the vector field along the orbit. That gives me a matrix, and this matrix equation is the perturbation equation around the orbit. It's a linear time-varying equation. I solve that linear time-varying equation for my initial condition, and I will find out how my perturbation evolved in first order. Why is this important? Well, all the notions of local stability that we have are basically based on this idea. So all your linear systems theory is just a special case of this, where the trajectory happens to be easy. For hybrid trajectories, if you have some guard on the way, you can evolve along the trajectory until you reach the guard, and then you can evolve after the guard, but something special can happen at the guard. Why is that? It's because the vector field is pointed one way before the guard, and it can be pointed at a different angle to the guard going out. And that little corner in the vector field produces an impulse, produces an instantaneous change, and that change is called the saltation matrix for that guard. It has this form. It looks like an identity plus a little product where I'm thinking of this, the gradient of h here is the function that defines the guard. This is a row, this is a column. So this whole thing is a matrix. And the matrix depends on the difference on the difference on the vector field from both sides as I take the limit to the guard. Okay, so this saltation matrix really tells me how I deal with hybrid transitions when I have dynamics that are hybrid. And if I have a bunch of events, I just take the matrix product, ordered, by the way. This is not an unordered product. It's an ordered product in the order that the transitions happened. I just multiply the saltation matrices, and that tells me how the sequence of hybrid transition events affected my perturbations. So this is what's going to decide whether the hybrid structure of this problem changed any of the stability properties, because everything else was smooth. Right? When we are within each domain, we have the standard linear time varying structure. And when we have this sequence of hybrid transitions, they can influence the outcome. So the way to understand what happens there is we use this sample vector field that's zoomed in, and we compute these projection operators, and we can use this to actually very quickly integrate multi-contact dynamics. To give you a sense of what I mean by very quickly, it's actually really simple to do. So this is in a paper we published a couple of years ago now. The entirety of the Python code that does the computation of taking an initial condition through an arbitrary collection of hybrid transitions to its outcome. Okay, it's literally 11 lines of Python code with about 40 pages of math to prove that they're correct. So it's one of those cases where the problem is a lot simpler than it looks on the surface. So let's look at an example. Here's an example. We have a sort of two-legged system. It's a 2D problem. It can tip. It has two legs that can hit the ground. Both legs can hit the ground at the same time. We have a spring damper that activates on ground penetration, and the spring dampers can be different for the different legs. So you can see we can have some interesting dynamics here where there's a double collision point, and if we tip slightly on one side, one dynamic takes effect. If we're tipped on the other side, another dynamic takes effect. And without damping, the system is clearly continuous, but with damping, the velocity is actually going to have a different value the moment you hit the ground. Okay, so it can create a discontinuity in the vector field. So if we take this system and compare the two-legged chair bouncing on the spring damper ground, compare using a conventional integrator, which detects the events, runs an OD integrator, detects the event, solves for the collision point, integrates to the next surface, solves for the collision point, then solves out. Compare that with using our approximation, we get a speed of about 1400 by using our algorithm. If we do that with a three-legged chair, we get an improvement about 43,000 times faster. It's just spectacular. It's just the difference between dealing with a hybrid system and basically dealing with a smooth system. Okay, it's just you don't even feel the fact that you're working on a hybrid system. And so you'd say, okay, so it would be nice to have a general purpose event selected system integrator, and we're developing one. And I'm going to give you one slide of sneak preview from what's happening there. So Marion developed an event selected integrator. It has some predefined mechanism of detecting that it's close to a guard, and when it's close to a guard, it uses the projections to pop itself through the guard. We took a very simple spring hopper and compared our simulation with MuJoCo, which is a pretty popular mechanical simulation tool. And you basically see that we have sort of the same errors as MuJoCo. That is, we don't get the perfect analytic solution either, but our error is comparable. Our integration error is order 2. So we behave like a second order integrator in terms of the order of ODE integration. But we scale much, much better than MuJoCo, and I'm not going to show these results here. Basically, you can change the number of collision surfaces to hundreds, and nothing changes in the performance of our code. So let's get back to mechanics. Now consider a mechanical system with these conditions. So mechanical systems are generally second order, but let's say that our guards only depend on position. And potentially they could depend on velocity as well, but let's say our guards depend only on position. Most manipulation and legged locomotion problems are like that, right? Whether you make a contact or not depends only on position coordinates, not on velocity coordinates. And the other thing is, let's assume that the situation is the one where we have additive effects. Okay, so this is a situation that other people looked at as well, but it's fairly common that what happens is when you establish a contact, you add a force, and these forces are just an additive effect. It turns out that then the saltation matrices look like this. You can write the product, you can expand this product, and then you discover something interesting, that because the guard depended on position, but the change was in force, the only non-zero term is off diagonal, which means that when you take products of the guards, they're going to be zero. So all the higher order terms annihilate, and you end up with a sum. Now, why is that interesting? Because the sum doesn't depend on the order at all. So what this means is, it's a very strange result, but what it means is, the order of collisions didn't matter. You're going to get the same derivative. So even
The result is exact.
it's
Or,
exact.
okay, not
So-
after truncation.
Yeah, this is not truncation. This is an exact
Okay.
collapse. Only the first order term, which is the sum, survives this product. So this means that the order of collisions didn't matter. So this thing that everyone's worried about, if we have so many combinatorial complexity of collisions, actually doesn't matter at all for this class of systems, which was a real surprise to us. So this is the surprising smoothness I'm talking about, because this means that all the pieces of that Boulegan derivative are the same matrix, which just means that there's a conventional derivative there, a matrix derivative. These systems that we would have thought are piecewise are not piecewise, they're just C1 smooth. So instead of being CR smooth as the original functions, you only get C1. You lose all the high order smoothness, but you still have C1 smoothness, which means you have linearization. You can use linear control. So this is them's fighting words, as they say. This is math. Does this actually happen in a real robot? Well, what sort of robot would we need to do to test this? We need a robot that could have different sequences of hybrid transitions. The only way you can get different sequences in a meaningful way is you have at least 3 event surfaces, because then you could have orderings that are not just A, B, or BA. So we wanted to build a 3-legged hop. These are our first attempts. We put some spring legs, and these hoppers hop pretty nicely. But we discovered something kind of annoying, and that is, even though they look like they're hopping, that's a lie. What they're really doing is they're losing all their kinetic energy on the collision with the ground, and then the motors are regenerating all the energy for the next hop. So if you took this robot and ask yourself, does it remember its history? Does the initial condition actually survive the collision? No. The initial condition is completely annihilated. Your perturbation energy goes to 0, and then you're regenerating an entirely new hop. So we tried to improve by changing the legs. These legs have rollers now, different kinds of springs.
Yes.
Only position sensing on the motors. Even better wheel to prevent friction because we thought we were losing all the energy to friction with the ground. We tried a bunch of different springs. So these are pairs of leaf springs with different kind of bracing in between them. This is a high-speed camera. This one buckles completely. This one buckles less. This one doesn't buckle at all. We're trying different kinds of springs to try and achieve recovery somehow. All of that didn't work until we did this experiment and it made us realize what's going on. So what you have here is spring clamped to the table, spring clamped to its attachment, spring attached to the motor, motor turned off. The motor is killing all our energy. Basically, whoever told you that series elastic actuation conserves energy was halfway lying, because if you have a PID controller on your motor, what's the PID controller doing? The D term is pretending to be a damper, and it's taking all the energy out.
What's not pretending? It's taking all, that's its job.
Yeah, its job is to take the energy out, and so that means that you're losing all the mechanical energy in your system, and that mechanical energy is an expression of your initial condition. And so if we want to have dynamics that actually go through a collision and survive that collision to have some meaningful outcome so that we can prove that this theory works, we need to do something different. And that something different is this guy. So the cables preload the springs, but when the springs hit the ground, they're interacting with the ground without a motor in the way. And so this robot conserves slightly over 40% of its energy from hop to hop and allows us to do the experiment, basically, that we needed to do. So that was 1.5 years of our lives to figure out where the energy was going and how to build a hopper that was actually not nonsensical. I suggest parallel elastic actuation if you want to conserve energy. And so this is what you get in real time. And so on this robot, we have 3 markers on the body of the robot, 3 markers on the legs, and you can sort of get a sense of what the dynamics are. This is the body Z, and this is the distance between the body and each of the legs. You see, as the robot is pulling up, it's also pulling the legs up. Then falling down and colliding.
Are you guaranteed periodic motion here?
I mean, the periodic motion comes out of the dynamics. So no, there's no guarantee. What the robot is actually doing is as it lands on the ground, the cables go slack at a rate of about 10 hertz. We're pulling the motors for load. We realize the motors are unloaded. And so we push them down so the cable will go completely slack. And then at a certain time after that, we start pulling the legs back up.
And the command of the motors are same,
Position commands.
the same to the all motors.
Yeah, giving the same command to all the motors.
So there's no feedback.
The only feedback, I mean, these motors themselves have PID control. So they do.
There's no feedback based on the performance of the orientation. So
No.
why do you call it a motor?
Well,
It's not a robot, it's a
It's a hopper. It's a hopper.
it's a hopper mechanism with
So what would happen if you distinguish between motors?
so I will say, to make this interesting for the problem, we actually built a version of this where we put a different clamp on each leg. So the legs have different stiffness.
Asymmetry.
So that there's asymmetry, and I will get to that in just a bit, because that's
interesting.
because that's really necessary. Okay, so let's talk about how we analyze the hopper data. First, what is it that we plan to show? We want a hopper where we can show that each leg does something different. And we do that by showing that if you take the flow of the state of the robot from the collision of leg number 1 to some point a few frames later, but before any other leg is hit, the affine model of that flow is different statistically, clearly from the affine flow that's done by leg 2 and by leg 3. So there's no question that the legs do different things each leg. And then we want to show that by the time all 3 legs have acted, The matrix derivative exists for the map and it works for all combinations. And that will prove what we claim, that the flow is smoother than people think, even though it's made out of pieces that are different. Those pieces mesh together to make a smooth thing on the outcome.
Is there a boundary to the difference between there should be?
I mean, the boundary is the collisions of the legs. Those are the guards.
Properties of the springs?
And so
Springs are different.
the springs are different. You have
How different can they be?
they're different enough that you'll see it in a moment. Okay.
Because at some point they're going to lose stability.
So this is actually very robustly stable for reasons that I can get into. Yes.
You're talking about a collision.
Mhm.
Really, this is a very long time elastic deformation. And that itself is probably stabilizing to a certain extent. Because you have everything, it's not a collision. If you wanted to go to the limit that this was a very quick collision, you were talking about events that are close.
Yeah.
But those each event is developing, it's not like in collisions of rigid bodies where it goes through this arc.
I mean, right. One man's collision is another man's slow process. If I'm going at 1,000 frames per second, things look very continuous mechanics. And if I'm taking 10 frames per second, it looks like a collision. What I'm trying to do here is this.
This is the relationship between at least two.
What I want to show here is that I am allowed to throw away the collision in the sense that you're talking about and go to the time scale that I'm talking about and treat it as a collision. Basically to simplify the dynamics, that I don't need to do collisions on the millisecond.
But isn't it coming because it's very elastic?
No. So one of the things that's happening here, if what we had here were springs that are starting relaxed, nothing would be surprising about this, because the force would start from zero and ramp up, and then everything is what you expect. Because you have this sort of unidirectional gate, as soon as you release the cable, the force is pretty high. That doesn't happen. It's a good question. I think your intuition is right. If these started from springs at rest length, there wouldn't be anything interesting happening here. Okay. So before that, let me point out a couple of methodological problems, right? We have different collision sequences, which are different parts of state space. But if you try to build a linear model in one part of state space and compare it to a linear model in another part of state space and see the difference, the problem is that when you extrapolate, your confidence intervals get bigger and bigger. So a better way to do that is I'm taking the points here and I'm reflecting them into here.
Why linear models?
Because I'm looking for an affine model of my flow. So that's mean plus linear.
Okay.
I mean, I would love to do a higher order model, but that needs orders of magnitude more data.
Because the elastic deformation is large and periodicity, but go ahead.
Yeah, I'm happy to talk methods later, but I will point out that to get a tight condition, what you really want to do is take all the collision sequences and symmetry remap them into the same sequence so that you can see that when they're folded on top of each other, they become identical. That the only difference was the orientation. So what that means is if our initial cloud of points looks like this, we have a nominal name for each point, and we can sort of rotate everything and normalize everything. And after we do that, we can look at these sorts of data. So how do we detect our touchdown? This is the head position in millimeters and the maximal and minimum force. And what you see here is sort of the sporadic cycle that you have here, where the machine bounces, and we can look at these statistics and pick thresholds that basically allow us to detect when collision happen. And this is an actual picture for a data set written in impact time. So you have our pre-impact states of hundreds of hops, our post-impact state, and our transition events, the times at which each foot hit. You see, this is very similar to the diagram I showed you before that was purely illustrative of a 3D flow. We have before impacts and after all the impacts. And what we want to show is it doesn't matter through which sequence you go, you end up with the same linear model. So how do we do that? Well, let me first show you in micro what happens here. So take the z velocity of each leg. So these are these three lines, the three blue lines. Sampling at 100 hertz, this is sample number. You see what our data sort of looks like. Velocity is decreasing because this is gravity's rainbow, and then the leg hits the ground. We can identify the collision times. And what we do is we also look at the z position of the body, and that's very smooth, as you rightly point out, because this body is coupled to the ground through springs. So it just does this nice red oscillatory shape, and we can pick a threshold based on the statistics we saw before, and we're doing the impact from 444 millimeters is our starting point when z crosses that, and our ending point is z crosses 290, which is enough for all the legs to have hit the ground. And what we want to show is that the map from this initial condition to this final condition ends up being consistent no matter which order the legs hit. That's what we're trying to show. You can see that we can pretty reliably detect where the legs hit. Okay, so now let me convince you that each leg is different. So what we do is we split our data into training data and test data. These are, of course, results on test data. Leg three model trying to predict leg 3 behavior. Error tiny, similarly for leg 2, similarly for leg 1. But if we take the model of each of the legs and try and predict the other legs, we get pretty large error. So it's very, very clear that what each leg does to the dynamics as an individual leg is completely different. Right? They don't do the same thing. But if we do the input-output behavior, so this is a bit trickier, and I think the statistical methodology question here will be out. We'll not have time to discuss. But what we're doing here is we're doing total least squares regression. A total least squares regression, in this case on a 12-dimensional state space, is really looking for a hyperplane in a 12-dimensional hyperplane in a 24-dimensional space. And what we want to show is that we have 6 of these hyperplanes, one for each collision sequence. And what we want to show is that they're identical. How do we show that they're identical? Well, there's a way to measure distance between hyperplanes. It's called the geodesic distance on the Grossmanian. And we can look at the distance between these hyperplanes. And within our data, the distance looks like this. If you just take a single hyperplane with noise, the distance looks like this. If you take random data that is hyperplanes that aren't identical, that are just arbitrarily distributed, the distance looks like this. So you see that we're closer together than a single hyperplane with SNR of 10. Is this conclusive? No, we need to improve the statistical tests a little. But you can also see the log mean square prediction error training contact sequence versus test contact sequence. So if we train on all the data and test on all the data, this is the noise. And you can see sort of each contact sequence with respect to the other. So what have we learned from all of this? One is that multi-contact mechanics can be modeled with event-selected systems in a variety of ways. That the event-selected system models are much, much faster to compute. Right? I mean, the speedups compared to conventional ODE integrators were from the thousands to tens of thousands of times faster. It's basically taking these multi-contact problems from being computationally annoying and intractable to just behaving like a regular ODE. You just don't need to worry about them. And in particular, for event-selected systems where the force change is based only on position, the systems are actually going to be smooth in a place where we didn't expect them to be smooth, and you can just use your smooth theory and forget about all these event-selected systems. You can just say, I don't care anymore that there are multiple collisions. I can build my robot hand with 10 fingers and build a linearized model of the 10 figure of the collision around the simultaneous contact of the 10 fingers, and that linear model will work. That's it. That's what I wanted to say. Thank you for your time.
Okay, now time for question.
So your last comment tells me if I get it wrong. You can tell me if I got it wrong. Basically, because all these events happen and the order of them doesn't matter, you can come up with a constitutive equation for the total event and forget all the details.
Exactly. Exactly. That is exactly the point.
And one other question. If you were to replace the linear damper with a Maxwell damper, would you have any advantage? Because you wouldn't have a discontinuity.
Well, so I will point out that for changes, one sec. So this is allowed to have a damper. You're saying if I change the kind of damper?
Change the kind of damper. The
So what's
damper that you have is ones that says that there's a jerk in a velocity.
In series.
But if you had a spring with a damper in series, a damper in series,
That's
an actual model, and then you don't, it's smooth. Because the elasticity makes it smooth.
yeah, I understand. I mean, that just makes it easier to get smoothness, right?
Yeah, but would it help with, you mentioned there's a problem if you had the damper, so you dropped it out.
Okay, I mean, that would definitely help, but that sort of makes it also trivial. I think I should be very careful in what I say in terms of what the conditions are here. The forces here, the forces here, this is actually misleading. The forces can depend on x dot as well. There's not a problem with that. If you go to the paper, there's some detail. Yeah. So sure, it would help. It's actually not necessary. Yeah. Other questions? Yeah.
I want to say this is very interesting what you're showing, because we often make mistakes in simulations and we see correct results or almost correct results.
Yeah.
But I want to ask you about the stiffness of the problem. I think I assume that what you modeled with the 3 legs is kind of modeling the approach or something, right?
Well, the reason I was looking at this is because I see multi-contact collisions in animals, right? That's where I started from. Yes.
I was also better, if you remember.
Yeah. No, we're hatched from the same egg. Yes.
My question is that if if I understand correctly, so you're saying if we drag the ball, it doesn't matter how we contact it. However, but if the contact is very rigid, very stiff, so just touch it, it's going to fly away. We're not going to close it.
Then you won't meet these assumptions, right?
So where's the border?
The border is that. I'll say you can relax this in some ways, but the way I've presented this here, you need all the fingers to hit. And my promise to you is that you can write a single equation from 0 fingers to n fingers that's smooth. If you have a situation where you don't go to all n fingers, that will be a different equation. And that will be an equation for n-1 fingers. And that will be smooth for any order of those n-1 fingers. But all bets are off when you add the final finger.
All the examples that you show imply periodicity.
Oh, no, this is actually a local result. I'm using periodicity to get my n up for experiments.
The experiment.
But I'm talking about orbital derivatives. So it's just a piece of it.
This is just like a Floquet generator. So
Yeah.
this is you have orbital stability. But what happens if can you handle a non-stationary solution?
Yeah.
For instance, if your motors are not inputting periodicity into the dynamical system, and they're doing something slightly different, and you have incommensurable frequencies from existing, can you still use the event?
Yeah, and so as I'm saying, this is actually a local result. So it doesn't matter if you're periodic and you're just applying the same thing over and over again, or if you just look at some trajectory and you're applying it locally to one piece of that trajectory. What this is telling you is, let's say I have a trajectory and here it has some complicated multiple collision and then it continues on. If I take the map from here to here,
don't care about what
I
happened.
don't care what happened in there. And I don't need it to wind back in and go through that again for it to happen.
Maybe 1 minute. I think we have at least 4 viewers from home. If they have the courage to stay that long, maybe we should give them the right to ask questions. How many participants we have now? I can check it in the phone. Any questions from home? No, these guys understood everything perfectly. They don't have questions, I think.
Okay.
Please, I
Yes.
Would your method help, like the DM simulations they do for granular flow? Are many bodies that are interacting all the time, really complicated things.
Yeah.
Would this fit into that model, or it wouldn't be smooth enough to be conditions that you have?
So
Because they're smooth contact models, they use springs and dashpots and stuff.
I think that's a good question. I don't know enough about those models and the challenges in them to answer it. So I would need to understand what are the computationally, what are the challenges there? Because what this tries to resolve is a situation where you have multiple collisions and you don't know the order. How much does the order matter? Basically is what we're answering here. Does the order matter? How much does it matter? And in what cases doesn't it matter?
Well, a chaotic hopper, like a bouncing ball on an elastic deformation on a non-rigid surface, could be periodic. It could be chaotic. It couldn't be quasi-periodic, but if it's chaotic, then multiple legs, then my intuition would tell me that the order would matter. Okay.
Well, so I would guess the following. I would actually slightly modify that. And here's what I think would happen. If you can guarantee that the hops are large enough that every time it hits the plate, all the legs will hit the plate, then the multi-legged thing might behave like a ball. That is, the fact that it has multiple legs won't make things any more complicated. That's what I'm saying.
No, but there exists an attractor. An attractor can be periodic or quasi-periodic. I can understand that was the gist of your answer. But if the order of hits, which you demonstrated in the experiment, is that guaranteed? Because I don't see how to guarantee the additive effects, because the math here is for a specific dynamical system.
So
okay,
let me take your example a little bit further. Let's say I had 3 legs, and if I take the limit of these legs being very, very soft, you're absolutely certain that all 3 of them will have to hit
the legs.
All 3 of them will have to hit. If in addition the system was such that it has enough energy that I know that it will get released completely, that all the legs will be released, then the behavior from in the air to next time in the air won't depend on the order of legs, is what I'm telling you.
Okay.
If the legs are identical.
No, they don't have to be identical. That's what's surprising. They don't have to be identical. They could be completely different.
So the interim between the hits, because this is event selection, right? So you can be chaotic within the event. So the dynamical system solution will be non-stationary, and you will still have this, and it won't influence.
Yeah, the dynamical system solution basically will have a C1 structure. It will be smooth.
It will be smooth.
And you won't see the fact that there were different orderings of the legs. That will just disappear.
Last one, because we're getting out of time.
You said, assuming that while it's in the air, the legs come to their original deformation, they're free, because otherwise I could be hitting like this.
So if the legs come to a different situation, then the linearized behavior at the next impact will be different than the linearized behavior at the previous impact. No, what I'm saying is that model will depend on where the legs were in the air, but it won't depend on the order in which they hit the ground. Yeah. Okay,
Okay,
thank
we
you.
can maybe stop the formal session. I'm
Yeah.
stopping the recording, okay?
Yeah.
Thank you very much to Shai.